Alright, in this unit we're going to be talking about similar triangles. Before we actually get into triangles specifically, we have to generally talk about what does similarity mean and how to use proportions. It's just going to be helpful in talking about similar triangles. So similar figures in general, they have the same shape, but not necessarily the same size. So two polygons are similar if and only if their corresponding angles are congruent. The angles need to be exactly the same, whereas the corresponding sides don't need to be exactly the same. They're not congruent, but they are proportional. And I'll get into what that means in a second. So you can see we have these two quadrilaterals here with all of these angles marked as congruent, and we have this similarity statement saying that these two quadrilaterals are similar to each other. This symbol here means similar. You've kind of seen that before. You put that over top an equal sign and it means congruent. If it's just by itself, it means similar. So this also highlights the corresponding parts. Angle F is corresponding with angle K, or side GH corresponds with side LM. The order there matters. So if I say angle F is congruent to something, well, just based on that congruency statement, you can see that F and K are in the same spot, so angle F has to be congruent to K. You can also see it in the picture. Angle F and angle K are marked as congruent. Angle M is congruent to angle H. And now we're getting into how these sets of sides are actually proportional to each other. So side FG divided by side GH is going to be equal to, we're going to look at that other quadrilateral and pick out the same corresponding sides here. It's the same as the ratio between KL and LM. Alright, so really what I'm saying is that the ratio between these two sides of 8 and 16 is the same as the ratio between these two sides, KL and LM, or 6 and 12. 8 divided by 16 is a half. 6 divided by 12 is a half. That ratio remains the same when we compare two sides within a quadrilateral, or when we compare two sides between the quadrilateral. So this was really within one. FG and GH share the same relationship as KL and LM. On this last example here, now we're talking about side ML and side HG. So we're actually comparing between the two different quadrilaterals. We see that that has a ratio of, I'm just going to write it unsimplified, 12 to 16. Well, if I simplify that, that's just 3/4. That actually also highlights an important point. We're going to talk about this in a second, but that's really called the scale factor. If I multiply 16 times 3/4, that gives me 12. And that's true of all of these sides. If I multiply 20 times 3/4, that gives me 15. When I simplify that proportion, when I simplify that ratio, it shows us the scale factor. We'll talk about exactly what that means in a second. But we're going to be able to use those scale factors to find missing sides. So since the corresponding sides are proportional, we can use proportions, and we can use scale factors to find those missing side lengths. Before we jump into that, I just want to talk about how we solve a proportion real quick. So this is a proportion. It's just two equal ratios. 5 over x is equal to 37.5 over 30. To solve this, we're going to cross multiply. You multiply diagonally across. 5 times 30 is 150. And then diagonally across again, 37.5 times x. And then we can solve that equation just by dividing the 37.5 away on both sides. And we get that x is 4. What that's really saying is that 4 divided by 5 is the same thing as 37.5 divided by 30. We're going to solve one more that's a little bit trickier just because we have an expression on top instead of just a single variable. we're going to multiply 6 times that whole quantity, 6 times x plus 2, and then 2 times that whole quantity of 5x minus 2. So we really just have to distribute there. 6 times x plus 2 is 6x plus 12. 2 times 5x minus 2 is 10x minus 4. And then we're just going to keep solving from there. I would add the 4 over and subtract the 6x over, and then divide by 4 in the last step to find that x is actually, again, it's going to be 4. You can always test this just to make sure that you did this math right. You plug in 4 here, that would give you 6 divided by 3. Sorry, 6 divided by 2, which is 3. And you plug in 4 here, and you get 20 minus 2 is 18, which divided by 6 is also 3. So we did that correctly. So we're going to need to set up these proportions sometimes to solve for a missing length. QR is 15. NK is 12. And LM is 10. What's the length of SP? I'm going to call that X there. Alright, so I'm matching up these corresponding sides. The proportions, it kind of depends on how you want to set this up. I'm going to just compare this side to this side first. I'm going to say 10 over 15 is the same as, I started with the small one, so I got to start with the small one again, 12 compared to some x value that I don't know yet. Then we can cross multiply and solve for that x. 10x equals 180, so x equals 18. Always double check to make sure that that actually makes sense. This has to be bigger than this original one. Going from 12 to this new side, it's got to get bigger because this side also got bigger. And in fact, it has to be 1.5 times bigger. 15 divided by 10 is 1.5. 18 divided by 12 is also 1.5, and that's not a coincidence. This is being multiplied by 1.5 to get up to the bigger side lengths. That's called the scale factor. That's what we're about to talk about on the right side of this paper. Scale factor is the number that we're using to multiply to get to a new size. So a scale factor can be used to represent, really it's the ratio between two corresponding side lengths or two side lengths within the same triangle or figure in general. I want you to think about this as the multiplier. We always multiply, even if it gets smaller, we can multiply by a fraction, a number that's less than 1 or in between 0 and 1, and that shape is going to shrink down, but we're still multiplying. A scale factor is always thought about as multiplication. And the direction's going to matter here. Actually, these are the exact opposite. We're just asking, what's the scale factor from FGHJ, from this one to this one? So what would I multiply 8 by to get down to 6? Going from 8 to 6, actually that's what we already talked about, we would multiply by 3/4. Going the opposite direction, now we're going from KLMN to FGHJ. Oops, I didn't mean to erase that one. That's still 3/4. But now we're going the opposite direction. We're saying, what would we multiply 6 by to get us up to 8? And it's really just going to be that ratio flipped upside down. It's 4/3. And you could think of this as an equation where that's x, and then you divide by 6. 8 divided by 6 is the same thing as 4/3. All right, last one here. What's the scale factor from HG to FG? Well, HG is 16. FG is 8. So we're thinking about 16 times something to equal 8. Well, that has to be 1/2. So the order there is going to be important. If you said FG first, then it would be 2. But since we're saying we're starting with HG and we're making our way to FG, you're thinking about what was multiplied by that 16 to get down to 8. Well, that had to be 1/2. So really it's up to you which one you're comfortable with. You can use scale factors or proportions. They accomplish the same thing. For me, scale factors is pretty intuitive. I just think about what's being multiplied there, or going backwards, how would I divide? You can also set up the proportions. I think setting a proportion is very systematic, but I find scale factors more intuitive. It's really up to you which one you want to use to find those missing sides.